Hey, so I'm going to try and do a conceptual sort of video here that's going to go over chapter 11, which is our simple harmonic motion and basics on waves. So I'm just going to go through essentially the images that are in the textbook, the Pearson-Prentice Hall textbook, and hopefully that'll kind of get us rolling. So my intent is for this to be the initial start introduction to the topic. So to start off, I have an image of a mass that is connected to a spring, and in the top part here, okay, it is just static. It's not moving. There's no forces acting on it other than gravity and the normal force from the surface. But in the second one here, in image B, what's happened is this thing has been pulled to the right, and it is in this moment it is now being let go. And so the moment that it is let go, it will have a force that is trying to put it back to its equilibrium position being this central location right here. And so once you let it go, there is a restorative force by the spring trying to bring it back to this position here. Of course, once it actually goes past this position, it will have a fairly high velocity. And so it will move, because of that momentum, it will move straight past it, and it will eventually get to a maximum position here on the left, at which point it will have a restorative force to the right, and again want to go back to that equilibrium position. It is going to have the most force acting on it when it's on either of these two extremes. It'll have the least amount of force, in fact, zero force due to the spring, when it's at this middle position. So as its displacement x increases from the equilibrium position, the force will increase. So force increases with displacement, which is an important distinction to make. That's actually known as Hooke's law, where, and I think I'll get to this later, but F is equal to negative kx, where k is equal to the spring constant. It's essentially the stiffness constant of the spring. So the higher value of k, the more stiff the spring will be. X is simply the distance from the equilibrium position, and it's negative because if I were to pull the mass in this direction, the force is going to be acting in the opposite direction. So assuming that my force is in a positive direction, the restorative force by the spring will be in a negative direction. All right, so moving on a little bit, going into the idea of maximum displacement. So this being our equilibrium position, where there would be zero force acting on it, so that is your zero position. And if we were to pull this thing off to the left here and then release it, this is going to be the maximum, right? The center of that thing was going to be at its maximum x value. Again, here, once it goes by this central position, its momentum will carry it, and it will eventually get to this maximum position off to the right. And so when it gets here, it will again be at its maximum x position. And when it's at a maximum x position, we denote that as A for amplitude. Amplitude is its maximum x displacement. Notice that it will have its lowest velocity when it's here off on the sides. Its velocity will be at its minimum, and its velocity will be at its maximum as it's going in this direction. So let's say it's going from here, okay, it's going from here, and by the time it gets to, it's going to start moving in this direction due to that force. As it gets closer and closer to this position, the force will be decreasing and decreasing and decreasing, and when it crosses this point, the force will be at zero. But it will have a lot of momentum. It'll be moving very fast. So notice that its velocity max is greatest at this location here at the center, at the equilibrium position, and its velocity is zero here off at the ends. Again, velocity goes back to zero. If we were to hang a mass by a spring vertically, then so here would be our equilibrium position without the mass, and then here's our new equilibrium position with the mass attached. So the sum of all forces in the vertical direction would be 0, where you have mg, or negative mg if you want to look at it that way, acting down, and we have a value of kx acting up, positive, negative, it's all up to you. If this were positive, then this would be negative, or vice versa. So in this case, this would be negative, only assuming that the initial force acting on the spring would be positive. I prefer to do it the other way around, but whatever. So you can figure out how far it would displace given a certain spring constant and so on. I'm fairly confident that you guys will be able to figure it out from there. But let's say that you were to hang a mass from a spring. Once you let it kind of settle out, it's of course going to dissipate the energy over time. Maybe you can help it along, and it's going to have a new equilibrium position right here. And from this point on, you now measure this. This would now be your 0 position. You can then pull down on the mass and release it, and it'll oscillate up and down, up and down. It'll come to the same equilibrium positions, or the same maximum amplitude positions on either side, and it'll go from there. All right, so trying to move on. Okay, the energy that is in this system. So when you pull this thing off to one end, so we've pulled it off to the left, and it has lots of potential energy. This is known as elastic potential energy. It's built up in the elastic spring. The elastic potential energy, the elastic potential energy of a spring system is equal to 1/2 Ka squared, or kx squared if you prefer, but considering that if it is specifically at its maximum displacement, then rather than using x, we would use a, because a is at its maximum displacement. So that means that all of the energy of the entire system is equal to 1/2 Ka squared, versus if I wanted to, let me get rid of that. If I wanted to express the energy in the spring at just any arbitrary point in time, then I would have to use x. But if I'm looking specifically at its maximum displacement positions, then I would be using a in that case. Okay. So when it is at its central position, there's no force on the spring, and so all of its energy would be 1/2 mv squared. Where the v is at its maximum velocity. If I'm going to choose any arbitrary position anywhere in between, it's not at the center, it's not off on one end or the other, then the total energy of the system would be an addition of those two. The sum of all energies for the system would be equal to 1/2 mv squared, whatever velocity it has at that position. Oop, I meant to just erase the circle, sorry. And in addition to that, you would have the 1/2 kx squared. I would not be able to use a in this case because the x displacement is an arbitrary displacement. Okay, so I think that gets that kind of idea along. Notice that you have both potential and kinetic energy in that sort of position, and you would have potential versus kinetic at these extremes where it's at one side or the other, or if it is at the central equilibrium position. Okay, moving on. I think I screwed something up. Okay, here we go. So, again, I'm not really going into the math. I'm going to post the PowerPoint. You can go through the math, and I have other videos that talk about the math a bit more. I'm just trying to go through the concepts here. So, in this case, we're going to essentially mathematically be equating simple harmonic motion with circular motion. So what I want you to do is to look at this scenario where we have a tabletop system that has something moving around in a circular fashion. And so at this point in time right there, it has an object that is at that moment in time moving in this direction. So it has a velocity of v. And in fact, maybe I shouldn't express it that way just yet. So it has a velocity along the tangent. That velocity along the tangent I'm going to call v max. So just bear with me for that in a moment. In fact, perhaps the best way to explain that is to, rather than look at this position, instead I'll use blue. If I pick out this position right here, okay, forget about this one for a moment. If I pick out this position right here, if you are this person at eye level with the table, imagine looking at the object. It's a ball and a string or whatever it may be. So it's an object going around in a circle. At that moment in time, it would be moving to your left, and in your perspective, you would see it moving at its maximum velocity in your perspective. If the object was here and moving towards you, its left and right velocity would be 0. If it is in this position, it is moving to your right, and again, it is at its maximum velocity relative to you in your perspective. You have no depth perception here when you're viewing it from that side angle. So therefore, you're only noticing velocities in the x direction. You are not noticing any velocities in the y direction. So the only thing that you notice is this velocity here in the x direction. So imagine that you have this happening here, where at any moment in time, its velocity along the tangent is equal to velocity max, because here it is moving along the tangent, and that velocity,
please excuse me,
the velocity along the tangent is v max. And so if I here relate that velocity along the tangent to the velocity in this x direction perspective here and here, that would be the velocity along the tangent. However, the velocity here, the velocity from your perspective is the velocity in the x direction. So you would have to make a triangle where the hypotenuse of the triangle would be the velocity along the tangent, otherwise known as v max, and then the velocity in your perspective off to the left would be your velocity. That's just the x component of that velocity. So that's this x value here. So if you imagine this would be your perspective, at that moment in time, you would see it moving off to the left, and it would be the x component of v max. Okay. Hopefully that's some clarity. I do have a video that I'd like you to check out. I'll try and link it in the description, but I do have it on my YouTube playlist. I have a video of a bicycle tire viewed from this sort of perspective, where I turn out all the lights and I have a light bulb on that tire. And so from that perspective, you can only notice the x direction velocities. So check that out. That might be helpful. Okay, so now let's really get into wave motion and how that's related to simple harmonic motion. So here, with the mass oscillating up and down, we have simple harmonic motion. By the way, simple harmonic motion is essentially any motion where the restorative force is proportional to the displacement. So if this is the equilibrium position for this thing, it is going to oscillate between here and here. It's going to go up and down, and it'll do it in such a way to where the restorative force is directly proportional to its displacement, meaning that the farther it gets from the equilibrium position, the greater the force and the greater the acceleration will be. That is simple harmonic motion. So given that this spring is going to oscillate up and down, we're going to take a piece of paper, a large piece of paper, and we're going to actually make it go from our right to our left. And if it does that, let's say that we had some sort of marker, right? So, I have some sort of marker that is attached to the mass, and it's going to actually mark a line onto the paper, then that line, so let's say that you had pulled the mass upwards and the mass was, here's the mass. And so then you release it and the mass will go down and up. And when it does that, the paper is moving from right to left. When both of those two things are happening at the same time, you're going to get this sinusoidal wave. And I know you're going to yell at me and say it's a conoidal wave. It's cosine rather than sine. But hey, if you just shift at 1/4 wavelength, you would have sinusoidal, which is typically how it's described. That's hence the quarter wave. Speaking of simple harmonic motion and that restorative force, pendulums are simple harmonic motion. Kind of. In truth, pendulums, right? So if I have some sort of ball and a string, and then I pull it up to one side and release it, and it will go back and forth and back and forth. Is that simple harmonic motion? And the answer to that is only if your angle theta is small. Essentially, your restorative force, right, you have the mg acting down, and then you have the force of tension acting in that direction. And then if you were to vector add those two together, you would get the sum of forces acting along this direction here, that it's actually, in that direction or in that direction and so on. So the restorative force is proportional to sine theta. And so since the sine of theta, as long as theta is small, if theta is small, I don't know what I'm writing, small, then if that is true, then sine theta is approximately equal to theta, which means that as long as theta is small, then yes, it will have that proportionality between the force and the displacement. So only if theta is small, so 5, 10 degrees or so, will the restorative force be proportional to the force, be proportional to the displacement, excuse me. So it will be simple harmonic motion if theta is small. Once theta gets above about 15 degrees, then it starts to really be no longer negligible, and then especially once you get up to like towards 20 degrees, it can be fairly egregious. You're looking at something like a 7-10% difference, and at that point, even in a classroom setting, you would be able to fairly easily see that it's no longer negligible. This is damped harmonic motion, so there's, this is essentially what you would expect to see with a spring over time, that as time goes from left to right, you would see that the spring motion would dissipate over time. I can have a spring with a mass on it, and I pull the mass down, and it'll go up and down. But as time goes on, it's not going to go up and down as much. Now, if I had a fairly friction-full system, then it's going to look something like this. You can have even a system that's over-damped, where it would look something like, maybe something like that, where it, and that's essentially what happens with shock absorbers in a car. Those are purposely over-damped. So don't think it's necessarily a bad thing. It depends on what you're trying to get at. So that's damped harmonic motion and over-damped harmonic motion. Under-damped would be, what it sounds like, where there's essentially no damping at all, which again isn't necessarily good or bad. If you think of a car, again, if the shock absorbers go bad, if you've ever seen an old Cadillac, sometimes those things will be under-damped, where it hits a bump and the car just keeps bobbing up and down, and that's not something you want in that scenario. So we're going to create a wave pulse, just a singular wave pulse. So you're going to take your hand up, shift it down, and go back to your equilibrium position, and you're going to have this wave pulse that's going to propagate from left to right. Notice that each molecule of the string is simply going to go up and down. It does not move left to right. So make sure you're clear on that, that the particle movement is perpendicular to the wave movement. The wave moves left to right. The particles of the rope will move up and down. They are perpendicular to each other. That is known as a transverse wave. So regardless of the type of wave, which I'll get into more in a second, we are going to always draw it and represent it in this transverse wave sort of way because it's, well, it's visual, it's easy to understand. So the high point of the wave is going to be known as a crest or peak. The low point is going to be known as a trough. The difference between its equilibrium, or the midline, and a crest or trough, so this height difference here is going to be known as amplitude, not wave height. Wave height would be this, and that is not something we are concerned with in physics. You would only be concerned about wave height if you were a surfer. Between the lowest point and the highest point, you would be concerned about a 100-foot wave in that case, because that's how much water is going to topple on top of you. But in our case, we're concerned about how much energy there is between the equilibrium position and a high point or low point. That is known as amplitude. The distance between any successive points on a wave would be known as wavelength, and that is drawn like this. That is lambda, the symbol lambda, and that is wavelength. Now you can measure, I often will go from peak to peak, or crest to crest, or you can go from trough to trough, and that distance is going to be wavelength. It is measured in meters. It is a length. It is the physical length of the wave itself. And when you go from one point to another point that repeats itself, not only is that the wavelength, but we would also consider that to be one complete cycle of the wave. Okay, so those are the parts of the wave. Do not forget that wavelength is measured in meters, and we can have lots of different waves of lots of different lengths. Depends on the type of wave. So electromagnetic radiation, for example, light, can come in all types of sizes. You have radio waves, which can be as long as hundreds of feet, maybe 500 feet or so. And it can be, of course, I'm not measuring in meters, so let's say 1 to 200 meters might be radio waves, AM radio waves specifically, or ham radio waves. And then Bluetooth signals, those are going to be in, maybe a tenth to half a meter, that kind of thing. And then microwaves are basically part of the radio wave spectrum that is going to be about a tenth of a meter, about 10 centimeters. And then you can go as small as, let's say, visible light would be between 400 and 700 nanometers. Remember, nano is times 10 to the negative 9th, so that's fairly small. And then you can go as small as gamma rays, which are, in the picometer scale. All right, so moving on. Okay, so a compression or longitudinal wave versus a transverse wave. This here is a transverse, and this here is a longitudinal. I'm going to probably spell it wrong, I'm sorry. Longitudinal wave. And so what happens here, if you were to take a slinky, in the top one, you would do the same thing as what we did at the rope. You take your hand, you shift it up and down or side to side if you're viewing from above, and you would get this transverse wave where each individual particle is moving this way, but the wave itself is moving this way. They are perpendicular to each other. But with a slinky, you can also take your hand and you can shift your hand this way and then back. And in doing so, you would create a compression. That compression would propagate left to right, and you'd also have what's known as a rarefaction, or an expansion is what they're calling it in this case. But you generally will have compressions and rarefactions. The rarefaction is what it's called with sound specifically, because sound moves as a longitudinal or compression wave. And so if you can think about it, if a steak is undercooked, it has less cooked, it has been less cooked. So a rare fraction is when there's less pressure. So imagine that moving from left to right. The compression, the spacing between the slinkies would actually propagate left to right, and you have each individual slinky section would move to the right and then back. It actually would have simple harmonic motion to that individual part. If you have a slinky at home, you should try it, by the way. All right, reflections. So if I have a incident ray coming in this direction, and it's going to have an angle of theta relative to the normal, then it's going to leave at the same angle. That is known as the law of reflection. These here represent the wave fronts. So if I have a wave that is going like this, it's going in that direction. Perpendicular to that, I'm going to draw a wave front. So these are the wave fronts. These are typically going to be the peak or crest of the waves. And then somewhere in between, you would have the troughs. We usually don't draw the dotted line, but I'm trying to make this point that the solid line is the wave peak, and it's that wave coming at you. And perpendicular to that, we can draw the ray version of that wave. And then a ray drawing is typically what we do if we're talking about reflection or refraction, which I'll get to here. Principle of superposition basically says that two wave amplitudes can add together. And so if this wave here is propagating left to right, and this wave here is propagating right to left, they're clearly going to hit each other. And so as they come towards each other, and I wish there was a couple more parts to this, but as they come towards each other, when they get to the same place at the same time, since this one has as much positive energy as this one has negative energy, they will cancel each other out, and the entire string will momentarily go flat. But once they move past each other, this one will have moved to this location, and this one will have moved to this location. They will go right through each other as if neither one is there, and only during the time when they intersect at the same space at the same time will you see that interference. So this here would be known as destructive interference. And when you have two waves that are both positive amplitudes and they hit the same spot at the same time, you suddenly will get this peak that will happen really quickly, and then they'll just move right past each other. And that is known as constructive interference, when the wave amplitudes will add together. This happens, and this is superposition. Superposition meaning the two things are superimposed on top of each other and add together. Okay, so with this, if I have a string, so let me just kind of draw, and then I have some sort of the string is connected to something sort of like hard on the other side. It's a fixed point. So I'm going to create a wave pulse here, and it's going to propagate right to left. And as that propagates right to left, how do you like that drawing? It's going to hit, and then if this is a fixed point, what will happen is it will flip over. It'll actually flip down, and then it'll come back on the opposite side, and it'll come back to you like here. Okay, that's what will happen. If this is a fixed point, if it was loose and there was just nothing there, it would actually, let me see if I can flip this thing around again. So it would come down and then it would come right back to the same side. But if this is a fixed point, it'll come down, it will flip, and then it will come back on the other side. So what I want you to do is imagine something. Okay, let me actually copy this thing. Copy. And paste. There we go. Okay. So imagine you send two pulses, not one, but two. And so you send a pulse down, and it goes and it hits, and it reflects. Okay? It reflects and it comes back. And then you decide to send another pulse. So this one is going to be your second pulse, and you send it down. and what's going to happen when they intersect. So the principle of superposition says that they will interfere with each other. So depending on how and where they interfere, what will happen is if you get the timing and tension just right, then they will interfere in such a way to where they will cancel each other out here. Excuse me, sorry. Stumbling on my words. And so if you send wave after wave after wave, what will happen is that one particular location, you will consistently have destructive interference because of that interference between the first wave and each successive next wave. And so that is what I'm expressing here. That at this location, you will consistently, as time goes on, you just keep doing it, and there will be no movement here whatsoever. This is known as a node. And then at this location, you'll notice that there's a maximum amount of movement. That is known as an antinode. And so the simplest standing wave where this occurs that you can have would be where you have a node on each end and an antinode in the middle. Again, this is where you have a fixed point on each end, essentially. Nodes on the ends, antinode in the middle, and this would be known as the first harmonic. Some of you music people might start geeking out a little bit here on me. And so then each successive harmonic, you'll have, the second harmonic has two antinodes and so on. And that, again, is if you have these hard points. That's what happens with a string. If you have like a wind instrument, and you're talking about sound, let's say you have a closed end and an open end, then your first harmonic, the fundamental as it's known, would look like this, where the sound goes in and the wave would look something like this. And if you notice, only part of the wave is actually inside of the tube. And we'll get more into this in the next chapter, but you can kind of draw out the rest of the wave, and this would actually be one full wavelength. Okay, you notice that? And so in the fundamental, only 1/4 of the wave would be in the tube. You have an antinode at the open end of the tube and a node at the closed end of the tube. But we'll get more into that another time. Refraction. Do not confuse it with reflection. Refraction is when there's a change in wave speed and the angle will change. Okay, so the way that I typically will describe it is, what if you had a series of, viewed from above, we have a bunch of people marching. Okay, so these are all people in a marching band, okay, and they're all in line with each other and so on. And so they're viewed from above, and they're all going in this direction. Okay, each one of them is going in that direction. And then they come across some sort of muddy field, right? So here's a muddy field, and this part here is the concrete path. And so they're all walking in this direction together, shoulder to shoulder. And the rule is that they have to stay shoulder to shoulder. See if this thing is going to work for me here. So when these guys hit, this is actually going to work well. So when this first line hit, this guy here is going to get slowed down because he is hitting the muddy field first. Again, these two guys here have to stay shoulder to shoulder. So if this guy hits the mud first and slows down first, this guy is going to continue moving fast, but he must rotate in order for them to stay shoulder to shoulder. And the same thing must happen with the next guy in line and so on. So what effectively happens is an effect like this, where they turn towards the normal, okay, they turn towards the normal in a slower moving medium. Okay, so they're going this way, and then this would be the muddy field, and they turn towards the normal in a slower moving medium. If they were going the other way, just assuming that they go from a slow to fast moving medium, they would turn away from the normal. When dealing with light specifically, there's something known as Snell's law. Snell's law is a ratio of the speed of light in a vacuum versus the speed of light in that material. So since the speed of light in a vacuum is the fastest possible speed, that means that this value will always be larger than 1. The value of n will always be larger than 1. So if the value is like in air, it's, I think, 1.0001 or something like that. It's essentially 1. Then that means that the speed of light in that material is almost as fast as the speed of light in a vacuum. But the speed of light in a diamond, for example, which is why diamonds actually are so pretty, is that the index of refraction is somewhere around 2.45, I believe. And so that means that the speed of light in that material is 2.5 times slower than it is in a vacuum. So because the light slows down so much, the angle at which it bends is very extreme, which means, first off, not all colors will bend at the same angle. So what happens is it's essentially a prism. It causes light to diverge. It's dispersion is what it's known as. And so in a diamond, it causes lots of dispersion. The index of refraction is very high. It causes light to slow down really a lot. And so it causes the colors to separate. So if you want to know just how much this light is going to bend, then you would essentially just apply Snell's law. Snell's law is essentially looking at the ratio of the two different indexes of refraction. Let's just assume this is air, so this is 1. Let's say that this here is water. Light does move slower in water, and so it would bend towards the normal in water. Water has a value of like 1.33, I believe. And so you could then figure out what this angle is relative to the normal given this angle. So angle of incidence versus angle of refraction. Not reflection, refraction. Diffraction. Diffraction. So essentially diffraction occurs when there's an obstacle. So that here is your wave fronts, but they hit the obstacle. And so the wave fronts go around it as much as they can. And what happens is you wind up getting, if you can see it, you kind of get this, it's sort of a, I hate to use this word in this moment, but it's sort of a dispersion of energy. The energy, there's virtually no energy here. And so energy will always want to go from a point of high energy to low, and so it will try and fill in that gap. And the angle at which this does that, right? So here's the initial angle. In fact, here's the initial direction. And so this angle here is known as the angle of diffraction, and the angle is actually dependent on the wavelength. So a longer wavelength will actually diffract more. So it will fill in the gap more if it's a longer wavelength, right? So let's say that it's a long wavelength, it's going to look something like that, versus if it's a short wavelength, it's going to be almost straight, which is what happens with light. Light has a very, very small wavelength, and so you can barely tell any diffraction that occurs with light. But it does, in fact, happen. By the way, here's another point to that. If you are listening to you're going to the stadium and you can, go into a football game, what's the first instrument that you can hear as you get closer and closer to the stadium? The first instruments would be like the tubas and the drums, the low frequency waves, because those waves have a long wavelength. They're able to diffract and go around barriers like the hill that's in the way of the stadium. And so you would be able to hear those sounds first because they diffract more. And that should about do it. I know that was long. I'm sorry. I'm just trying to hit all of the general concepts there so that way you can kind of run with it at least a little bit. All right. So hopefully that kind of does it. And stay safe. Be healthy. Have a good one.